This is mini lecture 19, and we're going to start solving what we call first order circuits. And I will define shortly what that is. We've spent time introducing the inductor and the capacitor in the last mini lecture. And namely, when we introduced the inductor and the capacitor, what we focused on really is the voltage current relationship for each element, for the inductor and the capacitor. And we noted when we look at the voltage current relationship that the voltage current relationship for the inductor and the capacitor is one that involves a derivative. Okay, so it is significantly different from what we've been doing. We've been looking at really resistors in terms of voltage current relationship. So it's a scalar relationship for resistor voltage is equal to resistance times current. And then now we introduce these two elements that their voltage current relationship is a derivative. So you can kind of see your differential equation content creeping into your circuit analysis, which is where we're heading here. I want to give you a fairly comprehensive look of where we're going. Let me share screen. This is, in essence, this represent, and when I mean this particular outline represent the content for about 3 weeks worth of lecture and work. Okay, this is what I call the second major component of circuit analysis. This is what a lot of textbook, the transient analysis portion of the course. What do I mean the transient analysis portion of the course? We spend the first month and a half working with constant sources with resistors. So everything is constant. We essentially learn mesh and nodal. We develop 3 equations, 3 unknown, 4 equations, 4 unknown. We could put this linear system in our calculator and come up with either node voltages or mesh currents. Okay, so these relationships essentially are scalar relationships. Here come the inductor and the capacitor with their derivative relationship for voltage current. All right, so we're going to have to learn how to we assume that into mesh and nodal. So today we're going to start what we call first order circuit. We're going to very quickly see here. We're going to define, and then we'll define first order circuit as a circuit that has a one storage element shortly. So generally you'll hear me say RL and RC. That doesn't mean there is only one resistor. It just generally means there is either one inductor or one capacitor. Today's lecture in particular is going to focus on this particular section right there. We're going to focus on first order circuits, and we're going to focus on circuits that have zero input. All right. And the reason we're going to look at that, we're going to look at circuit where you charge the inductor or the capacitor, and then you disconnect the source and see what happened to that energy stored in that inductor or the capacitor. This is what we call zero input, sometimes called source-free circuits. Okay, so I'll talk a little bit about this as we get an example of that because it'll be more meaningful. So today's lecture is essentially that, and then we'll do more examples. We'll start looking at circuits that have responses that are essentially off and becoming on via switches. And then eventually we're going to get to second order circuits where we put 2 of those elements together. And so you can kind of feel when you see that page, when I say first order, I'm hoping it clues you in first order differential equations. And when you see second order at the bottom, you're going to basically, I'm hoping you think second order differential equation, and that would be accurate. So let's begin our conversation with first order. I'm going to use a document camera to be a little bit more detailed, if you will, than PowerPoint allow me. So again, before we solve what we call resistive circuits, sources, and a bunch of resistors, okay? And the sources were constant sources, and we come up with 4 equations, 4 unknowns, and we basically put them in our calculator and solve for these unknowns. For circuits with capacitors and inductors, we are not going to have a system that is nicely defined. we're going to eventually develop one differential equation for the circuit. So your goal going forward in this section of the course is to use mesh and nodal to come up with one differential equation for the circuit. So we're going to start showing you how to do this and describe these circuits here. Okay. So first order circuits, we look at first order circuits just to define that again as a circuit that has one energy storage element. If you remember anything from that lecture that we just had, lecture 18, inductors and capacitors have the distinct ability to store energy. I use the gas tank analogy. Gas in the tank is the energy stored in the inductor or the capacitor and then released later. They don't dissipate energy. They don't create energy. They are passive elements. So, but because of the way they function, they provide really interesting ability to create very creative circuits, particularly if you take more sophisticated, more advanced course in electrical engineering. So we're going to also, for this particular circuits, this is the differential equations that we're going to be solving. We're going to be solving a differential equation that's of the first order. We're going to standardize our differential equations so that the highest derivative, in this case, the first order, has a unit coefficient. So let's all agree that we're going to do this. And the case we're going to focus on is first order differential equation with constant coefficient C and a constant right-hand side. Now, the constant right-hand side can be 0 or it can be a number. But this is only that. So it's really the very first few couple weeks of your differential equation course that we're going to be dealing with. So I'm going to step back here and go to the document camera and talk to you what we're going to be looked at a little bit more detail. Well, before I go to the document camera, let's look at the solution to this first order differential equation, which essentially, in terms of first order circuit, that is all we're going to be solving. So the first case we're going to look at here, we're going to look at the case where we have 0 right-hand side. This is what Math 45 differential equation called the homogeneous differential equations. Okay, so generally speaking, there is a solution. If you remember your differential equation, there is a solution because there is some initial condition of V of t. All right, so the solution to this is a constant A, e to the minus c, and that's the same c. That's the same c that you find in the differential equation here, e to the minus ct. So we're looking at a dying function. We're looking at an exponentially dying function, and this constant A is the initial condition on the voltage. Okay, so we're going to say V at some time t0, for example, is equal to some value, and that will be the value A, for example. Okay, so we look at these circuits because energy has been stored in an inductor and capacitor, and then all of a sudden we're looking at what happened to that energy once that energy is being dissipated. So I'm going to show you these types of circuit that we solve, but I want to go to the document camera to give you a little bit more intuitive feeling and conversation about what we're doing. So I'm trying a new program to run my document camera, and I'm hoping that it's essentially not causing difficulty in terms of freezing. So I'm hoping this is a success here. So what we're looking at right now, again, we're looking at, oh, it looks like it froze. Okay, so we're looking at, again, first order circuits. With 0 input. Okay, that's the first case we're going to look at right now. And what am I talking about here? I'm talking about some circuit that has resistors, either an inductor or a capacitor. So I'm going to put one energy storage element. That's what that ES means, either an inductor or a capacitor. And then you have probably some source that connects to the circuit essentially via a switch. And that source can be current or voltage source. But what essentially this is saying, and I can put some time t equals 0 here, what this is essentially showing you is before t equals 0, this source is connected to the circuit, and at t equals 0, the source disconnect, leaving the circuit source free. And you can also have, obviously, dependent source in there as well. Okay, so the ES is either an inductor or a capacitor. Okay, so that's what that ES stands for. So what we're looking at, again, we have some sort of independent, and we're looking at constant sources, DC source. Okay, we're looking at a DC source here, either current or voltage. It connects to the circuit to some switch. And let's say at some time t equals 0, you disconnect. So it's like you unplug the circuit from a DC power source. That's what we're looking at here. But what happened in this circuit for t less than 0? For t less than 0, you are essentially charging up that energy storage, that inductor or capacitor. You're essentially charging that. So we're going to look at how do we solve circuit like that. So we need to solve for t less than 0 first. And that's going to provide us our initial condition. And then we solve for t greater than 0. And that's going to give us our differential equations, which we're going to solve. Okay, so this is the process I'm going to show you. We're going to begin with the simplest example. I'm going to show it. I'm going to essentially solve it on paper. Okay, and then you're going to see how that plays out with increasingly more complicated circuits, essentially. So let me go back to the computer screen. So again, we call this response when the right-hand side is homogeneous, when the right-hand side is 0, we call it the natural response. In your Math 45 or your differential equation courses, it is what they call the complementary solutions, which is when the right-hand side is 0. That's going to be our natural response in electrical engineering. So I want to show you two ways that you can formulate circuit solutions essentially in this class. You can formulate the circuit solution in the top left, which is more like a math formulation, which says, given some initial conditions, say VC at 0, VC being the voltage across the capacitor, given some initial condition, solve for the voltage VC of t and the current to the capacitor for t greater than 0. This is more of a math formulation. Once in a while, you will see it in your textbook and in homework assignment. Most time, though, you're going to see the bottom right. The bottom right is more of an engineering formulation. In other words, you have a battery, a DC battery, that's what that means here, that has a value V naught. V naught is a set value, it could be 12 volt. It is connected to the circuit via a switch. What this switch is saying essentially is that it is connected, and at t equals 0, the switch opens up. That's what the arrow, that orange arrow you're seeing, tells you the action of the switch at the given time t equals 0. So the switch opens at t equals 0. So at t equals 0, the switch opens, and you have the circuit you have at the bottom, at the top left. So before t equals 0, you have a different circuit. So I'm going to take some time. I'm just going to actually go on paper and solve this and talk about it in a way that's pretty comprehensive. And then we'll go back to the PowerPoint slide. So I redraw the circuit on the document camera from the PowerPoint, and then I reformulated the question here, because you're going to get these types of questions more often than not. It's giving you a circuit, and it's asking you calculate, in this particular case, VC of t and IC of t for all times. Okay, and then this is the circuit. Here again, the circuit has a particular switch. That switch is closed. So the battery V0 is connected for t less than 0. And at t equals 0, it opens up. So whenever you see that, you need to solve before the switch action in this particular t less than 0 and after the switch actions. In this particular case, t greater than 0. So we have two circuits we're going to solve. We're going to solve the circuit for t less than 0, and we're going to solve the circuit for t greater than 0. That's the first point that's really important. So for t less than 0, what do we have? We have essentially the battery, the switch is connected, the capacitor is there, and the resistor. Okay, so this is V0, this is the capacitor, VC is there, and then IC. Okay, that's for t less than 0. So what we're seeing essentially here, this circuit has existed like this for a very, very, very long time. All right. So this is a circuit that's sitting with a DC source with a battery that's constant. That's what this is, a battery that's constant of value V0. All right. So nothing is changing here. Remember, for the capacitor, the current of the capacitor is C dVc dt. So if everything is constant, the voltage is constant, the current is 0. Because everything is constant here. There's nothing changing for t less than 0. Now, once the switch opens up, that causes a change in the circuit. That won't be true anymore. But for t less than 0, everything is constant in the current. So the circuit we actually solving is this. The battery, the capacitor looks like an open circuit with a voltage VC across it, and the resistor R right there. Okay, so this is the circuit that we're really solving. The capacitor looks like an open circuit because if there has never been a change for a very, very long time in any sources, then everything is constant. So the capacitor current is 0. So we model that by an open circuit. That's how we model the capacitor when it's been sitting in a constant source system circuit for a very long time. And you can see in this particular case, VC at t less than or equal to 0 equals 0. Okay. So for this particular case, it's fairly simple because that's the circuit we solve. So for the first time period, in this case, t less than 0, you typically have a circuit that doesn't have a capacitor because we're looking at circuits that have constant sources with switches that are switching them either on or off. So that's the circuit for essentially t less than 0. Now for t greater than 0, okay, the circuit we have is simply the capacitor in parallel with the resistor. Okay, the capacitor in parallel with the resistor because this particular source, the switch opens up, so it gets disconnected from the circuit. Okay, and I'm going to basically do a nodal analysis here. Node here. This is a 2-node system, very simple. So I'm going to have IC here. And then I'm going to call this node VC, and I'm going to put my reference node right here. And I'm going to put a resistor on my current. I'm going to call it IR. Standard nodal procedure like we've done before. Select my nodes, select a reference node, identify the node, select the reference node, label the other node. In this particular case, it's only a pair of nodes, so the reference node is here. So this node is VC. So all I'm going to do now, I'm going to do KCL at VC. Okay, which is what? Which is IC plus IR equals 0. Okay, that's my KCL equation at VC. Okay. Then I do Ohm's law for my resistors. Ohm's law for my resistors. I only have one resistor, so IR is VC over R. I use my Ohm's law into my KCL equation. And when I do this, what do I get? I get IC plus VC over R equals 0. Okay. So at this point, I've basically been doing a basic nodal analysis. I haven't really touched the capacitor at all. Now I'm going to deal with the capacitor. For the capacitor, I'm going to say IC is C dVc/dt. Okay. That's the relationship for the capacitor, the current and the voltage following the passive sign convention. I'm going to use, wherever I have IC, I'm going to use this. So put that in there. So what do we get? We get C dVc/dt plus VC over R equals 0. You can start seeing the differential equation kind of materializing. I wanted to do this part really slow and on paper instead of on PowerPoint, because while this is a very simple circuit, it's 2-node, it actually shows you the entire process. Okay. The only thing I have to do here is normalize. And I normalize by dividing by C. It's because I want the highest order derivative to have a unit magnitude. When I do that, then I get dVc/dt plus 1 over RC VC equal to 0. Okay. So that's the process. So I'm going to kind of review this a little bit, and then we'll go back to the PowerPoint slide, essentially. Okay. Again, when we have a circuit with a switch, in this particular case, we need to note the switch time. The switch time is important. And whenever you see a switch, it should clue you in. I need to solve the circuit before the switch. I need to solve the circuit after the switch action. Okay. And we also solve the circuit sequentially because we need the initial condition. So for t less than 0, this is the circuit we have. So this circuit, we have to recognize this circuit is a DC circuit. It has a source that's been like that for a very, very, very long time. It's a DC source. Okay, it's a constant source. So when capacitor or inductor, but when capacitor essentially see a constant source for a very long time, it behaves like it is an open circuit. It lets no current through by virtue of its current voltage relationship. Okay, so we model this circuit for t less than 0 like this. The capacitor behaves like an open circuit. We need the capacitor voltage because the capacitor voltage, we're going to discuss that a little bit later. It is the initial condition for circuits with capacitors because it's related to energy. So solving this obviously is fairly simple because VC is obviously, just in parallel with V naught. So it's just, I'm sorry, VC is actually V naught, not 0. VC is actually V naught, not 0. Sorry about that. VC is actually V naught because it is parallel with V naught. Okay. Then we solve the circuit for t greater than 0. When we consider t greater than 0, the switch actually opens up. So it disconnects this battery, the V naught battery. Okay. So what we have right now is this circuit here where the battery is disconnected. Then I proceed to do a basic nodal analysis, identify my nodes. I select the reference node at the bottom. I label the other node. It's only a pair node in this particular case. And then I put current on my passive elements. Here I only have 2 passive elements, the resistor and the capacitor. So I only have one node beside the reference node, so I do a KCL about it. So IC plus IR equal to 0. Then I do Ohm's law for all my resistor currents. I only have one resistor here. I use the Ohm's law into the KCL equations. And if I had more KCL equations, I would have used them into each one of them. That's what I get this. Then I write the capacitor current voltage relationship. You cannot flip that. This is something you need to know. Then I use that in my KCL plus. So this is what I call KCL plus Ohm's law. So I use the capacitor relationship in my KCL plus Ohm's law, and I get this. And then finally, I normalize. I normalize by divided so that I get a unit magnitude for the highest order derivative. And I get here. So I'm hoping this shows you the process. You're going to see that over and over again for different circuits. Okay, I'd like to see your process. In fact, I'm going to write this down for you in an announcement. I'd like to see that whether you're doing nodal or mesh. It's going to be the similar step that you see here so that you can come up with the differential equation right there. Okay. So let's go back to the PowerPoint. So back to the PowerPoint slide. This is essentially the differential equations that we have that I showed on the paper. And our initial condition again is VC at 0 is equal to V naught. V naught being the battery that was connected via the switch to this particular circuit here. So my expectation for you is that you basically write the solution for this differential equation. I don't expect you prove this thing. I don't need the proof. I need you to recognize you have a first order differential equation with constant coefficient. Okay, we talked about the C that we have, that constant we have, that 1 over RC is the constant, and the right-hand side is 0. So we're looking at a natural response, a complementary response back from your Math 45. So the solution essentially here, I just expect you to write the solution. It's VC for t greater than 0, because we're looking at t greater than 0, is a constant A, e to the minus t over RC. Okay. And then, of course, we solve for A by applying the initial condition. VC at 0 is equal to V naught. That's going to give us the value A. So the solution essentially, the voltage solution essentially for t greater than 0 is V naught e to the minus t over RC. If we want to find the capacitor current, we essentially differentiate the voltage and multiply it by C. And you got to remember what to do when you differentiate an exponent. You essentially take the coefficient of the exponent, bring it forward here. So it's minus 1 over RC times C times V naught e to the minus t over RC. So this is the current, essentially that. What you will notice essentially is that the voltage is continuous. The voltage essentially before t was 0, before t equals 0, it was V naught. And then but the current was 0 because the capacitor essentially operates like a switch. It's the change that makes the capacitor essentially allow current to flow. All right, the current was 0, and then it goes to minus V naught over R e to the minus t over RC. So if we plot these two things, this is what we see. We see that for t less than 0, the voltage essentially was V naught. The current, which is in orange here on our graph here, was 0. And for t greater than 0, we're looking at the voltage essentially exponentially decaying. And so is the current, but the current sees a jump. Okay, the current sees a jump. So in this particular case, how fast that this function decays, what we call the time constant tau. The time constant tau is RC for this particular circuit to measure how fast the solution decay. Just to give you a feeling here of what this is, if you shut down your computer, particularly if you have a desktop, when you shut it down, often you hear the winding sound. When you hear the winding sound and we shut down a computer, you're essentially hearing the energy stored in all the inductors and capacitors in the circuit dissipating out. That's what this is. This is a dying sound essentially for the voltage. Okay. So this is obviously the simplest example. It illustrates everything we need. We're going to do a little bit more complicated example, and even more so, we're going to practice this concept here, re-emphasizing the important features of these types of problems. So I'm going to do a second example with a little bit more complexity. It's going to have a little bit more unknown. I'm also going to go on paper to develop the differential equation, because I wanted you to get used to that, essentially work on paper, because I want to see the same work on your, in your either quiz or exam. So let's look at that. Okay, let's share screen. Okay. So we're looking at a circuit here the types of circuit we look at, let me just summarize where we are. We are looking at first order circuits. First order circuit means what? A circuit with either one capacitor or one inductor. Generically, I'm going to say one energy storage element. Capacitor inductors are energy storage elements, so with one of those elements, okay? And we are focusing this particular introductory lecture on circuits that have zero input. So we typically going to have a switch that disconnect at some point. In this particular case, t equals 0. So when we see a circuit like that that has a switch, what I want you to note is the time of the switch, okay? This particular case, 0 seconds, the switch is changing. And then I want you to know, how is the switch changing? Is the switch opening up, disconnecting? This is the case, the switch is opening up. That means after t equals 0, that 6 amp current source won't be connected to the circuit. Neither will be the 20 ohms, by the way, okay? So this is going to disconnect the left part of the circuit at t equals 0. So for t greater than 0, you won't have the left part. But in some cases in the future, you may have a switch action that looks like this, which means the circuit is being connected to. Okay, that's not the case right now, but you could have that. So you need to note the time of the switch action, this particular t equals 0, and what is the switch action? Is it disconnecting or is it connecting? Those are the two things that I want you to do. Then we look at, we need to solve the circuit for before the switch action, in this particular case, before t equals 0, and we need to solve a circuit after t equals 0, okay? And we need to do so sequentially. For t less than 0, so let's see what we got for t less. So for t less than 0, this is going to be connected right there. The switch hasn't changed yet for t less than 0. I'm going to have a circuit that has a constant source. Everything is constant. My 6 amp, everything is constant, okay? So the capacitor is going to behave like an open circuit, all right? So let's see what we have here. So the capacitor behaves like an open circuit. So you can see the capacitor current is 0 because it behaves like an open circuit, okay? And we need the capacitor voltage because that is our initial conditions. We'll discuss that again in a little bit more detail in the future, all right? So this is the circuit we solve. So for the first time period in these circuits, the time period here of t less than 0, we're looking at a circuit that is a DC circuit, no capacitor and no inductor, okay? Because the circuit is, these elements are in a circuit that has a constant source. So nothing is changing, so the capacitor behaves like an open circuit. If you had an inductor, it would behave like a short, like a wire. Okay, so in this particular case, it's a fairly simple circuit to solve. I can simply combine resistance here and use current division. I'm not worried as much about how to solve this. You could use mesh or nodal as well. There's nothing that says you have to use a particular method, but this is a basic DC circuits to solve, okay? In this particular case, again, I could combine the 20 and the 10 ohm in parallel. I could combine these two in parallel. Okay, so there's a lot of things I can do. I can combine in parallel, and after that, I can use current division and find I, and then from I can find VC as well. I need the voltage across the capacitor beside the current I, which is what you are required to calculate here. So again, not a ton here to do, fairly simple. We can use current, combining that and use current division. And once I have I, the capacitor voltage is simply 5 times I, okay? The capacitor voltage is required for the initial condition for the next time period, okay? So, and that's what we got here. So we got the capacitor voltage to be 4.8 volt, and the current that was asked is 0.96 amp. So even though I did not ask you for the capacitor voltage, you have to calculate the capacitor voltage, because that is your initial conditions, okay? So now I'm going to focus essentially on what happened for t greater than 0. So this is the circuit for t greater than 0. That part that was to the left of the circuit that had the 6 amp and the 20 ohms gets disconnected. So now the capacitor is back because that switch, having moved, causes a change in the circuit, so the capacitor has not seen something that's constant forever. So for t greater than 0, the capacitor essentially is back in the circuit. I'm going to go on paper and do this on paper so that you see the process that I'm trying to encourage you to see, and then we'll come back to the PowerPoint slide for the final solution. So this is where we are for t greater than 0. Again, the circuit we had over here is disconnected because the switch opens up. So that's 6 amp and the 20 ohm are no longer a part of the circuit. So I'm looking at this. And I'm going to solve this using nodal. I could also do so using mesh, but I'm going to do so using nodal here. This is a circuit. So I should say to you that this circuit can easily, I could combine the 10 and the 30 ohm in series. I could combine these two things in series and then combine them in parallel with the 5 ohm. And then I'm going to be back to a capacitor in parallel with the equivalent resistance. And then I'll be back to the circuit we just solved. Okay, I'm not going to do that because I want to show you a more general method. Okay, a method that has, this is going to be a two unknown method, even though it's, again, I could easily combine the 10 and the 30. All right, so this could be essentially 40 ohms with the 2 farad here, with the 5 ohms. And then I could combine the 40, that, and I get to this. So this is VC, 2 farad. And then this would be what? 40 times 5 over 45. Okay? So I could easily get there, and we're back to the solution we just had. All right? I'm purposely not doing that because I want to show you, because you're not going to be able to do this for most circuits. So I'm going to show you how you proceed with a regular nodal without combining. Okay? So just so you know that this is an option that exists. So what we're going to do here, again, let's put some nodes. I'm purposely not combining. Okay? Put my node here. I'm going to put my reference node right here. So I'm going to call this node VC, and I'm going to call this node V1. How's that? Okay? Just to show you a general approach instead of doing the combination. All right? So I'm going to say this is I1. I'm going to say this is I2. And this is I, and this is I3. Okay? So I put current on all of my passive elements here, which is my resistor capacitors. I label my nodes. I select my reference. Typical, I have no source here. I have no voltage source here, so I don't have to write source equation. If I had a voltage source, I would be writing a source equation. Okay, so this particular case, so I have essentially a two-node problem. So I'm going to do KCL at node V1. So what do we have here? I1 plus I2 equals 0. This is equation 1. Okay. Then I'm going to do KCL at node VC. So what do we have here? I2 equal I3 plus I. That's equation 2. Okay. These are my two KCL equations. So that's the first thing here. Okay. All right. Those are my KCL. If you had source equation, we need to write the source equations. We don't have any voltage source in this nodal, so we're not writing source equation. Then I do Ohm's law. And I want to see them separated just like I'm doing, folks. All right, I want to see those. So what are the Ohm's law here? I1 is V1 over 10. I2 is V1 minus VC over 30. And I is VC over 5. These are my Ohm's law. Passive sign convention when I write my Ohm's law. Okay. So KCL equations, then Ohm's law. Okay. Now I'm going to do KCL plus Ohm's law. I'm going to put the KCL equations into the equation Ohm's law, in the Ohm's law equation into the KCL equation. So what do I have? Equation 1 becomes I1 V1 over 10 plus I2 plus V1 minus VC over 30 equals 0. Okay. I can multiply this entire thing by 30. So what do we have? 3V1 plus V1 minus VC equals 0. That gets me where? That gets me 4V1 minus VC equals 0. That's my new one. Okay. Okay. Thus far, I haven't touched the capacitor. I haven't done anything with derivatives or anything like that. So I basically put my Ohm's law into my KCL equation. I'm going to do the same thing for equation 2. I2, V1 minus VC over 30 equal I3. I3, I'm not touching the capacitor yet, plus I is VC over 5. If I multiply by 30 to get rid of the denominator here, what do I have? V1 minus VC equal 30 I3 plus 6 VC. Okay, so what does that give me here? If I send everything in one side, I get V1 minus 7 VC minus 30 I3 equals 0. That's the new equation 2. Okay. All right. So my new equation 1, my new equation 2. I have not touched the capacitor. Okay. So I want to show you that process as methodical as it is, because I'm hoping that helps you essentially get, really a solid procedure down so that you can solve any problem. Now, write the capacitor relationship. For the capacitor, I3, that's the current to the capacitor, equal the capacitance to dVc dt. Okay. That's the capacitor relationship right there. So wherever I have I3, I'm going to put this in my two equations here. There's I3 here, and I don't have I3 here. Okay, so here and here. So this equation here doesn't change. So let me work here. Okay, so this, oops, sorry. So 1 stays as is. 4V1 minus VC equals 0. There is no I3. And 2 becomes what? V1 minus 7 VC minus 30 I3. So what do we have here? Minus 60 dVc dt equals 0. Okay, so that's 1 and 2. All right. At this point, I want you to look at how many equations you have. I have 2 equations and how many unknowns. I have 2 equations, 2 unknowns. So what do we do when we have 2 equations, 2 unknown? I can form one. I can solve from 1. I can solve for V1. Okay. So V1 is equal to what? VC over 4. And then use into using the second equation here. So what do I have here? Put there. I have VC over 4 minus 7 VC minus 60 dVc dt equals 0. And you can kind of see the differential equation coming to fruit. So again, if I multiply the whole thing by 4 just to get rid of the denominator here, so what do I have? VC minus 28 VC minus 240 dVc dt equals 0. So that is what? That is minus 27 VC minus 240 dVc dt equals 0. And you can see that I'm skipping no step here. Then I normalize by divided by minus 240. Okay, so divided by minus 240. So what do I have? dVc dt plus 27 over 240 VC equals 0. That is the differential equation for this problem for t greater than 0. Nothing is skipped here. Okay, so I want to take a moment to review what we did here. All right. Again, I purposely chose not to do the combination because many times you won't be able to do this. Although this, you could have easily done it and use the solution we just did. So I basically went on to doing a regular nodal procedure. Find my 3 nodes. Then I select the reference node. label the other node, and put current on my passive elements, namely my resistors and capacitor in this case. Okay. Then I don't have any source, I don't have any voltage source, so I don't have to do super node. I don't have to write a source equation. So basically I write one KCL equation at node V1, given the way I put my current. So it's I1 plus I2 equal to 0 because they're both leaving V1. And then KCL at node VC, which is I2 coming in equal I3 plus I. Those are my two equations. So I want to see your KCL equations. Then if you had source equation, I want to see the source equations. And then I want to see Ohm's law. And I want you to put the Ohm's law in, just like I showed. So the next thing we do is write Ohm's law equations for the current on our resistors. Passive sign convention applies whenever we write Ohm's law. So I1 is V1 divided by 10. I2 is V1 minus VC divided by 30. And then I is VC minus 0 divided by 5. That's what. Next step here is essentially what I call KCL plus Ohm's law. I basically bring all of the Ohm's law in my two equations, all my equation that I had, my two KCL. So this is equation 1 here. I bring in the Ohm's law, and then I put under the same denominator so that I can collect terms. So this is my node 1 right there, right? I do the same thing for equation 2. I multiply by 30 to get rid of the denominator. And then I get this equation after I put everything on one side. Okay. Now, after I've done KCL, Ohm's law, bring in the Ohm's law into the KCL equation, now I write the capacitor current voltage relationship. Don't write generic relationship. When you're writing this relationship, ask yourself, what is the current to the capacitor? In this case, it is I3. Is it following the passive sign convention? Yes, it is. That's why it's 2 dVc/dt. If the current was going the other way, it would be minus. So it is satisfying the passive sign convention, entering the positive terminal, times the derivative of the voltage, I3. Then wherever I have I3 in my two equations here, I'm going to put 2 dVc/dt. So again, I don't have I3 in my equation 1, so it stays the same. In my equation 2, I have I3 right here. So I have V1 minus 7VC, and then the minus 30 times 2 times dVc, that's the minus 60 times dVc. At which point I want you to look at here. This is a major point, and you should be able to get as many equations as you have unknown. In this case, 2 equations, 2 unknown. So we're basically now going to use substitution method. We solve for 1. We don't want to solve for VC in here because VC is sitting inside of a derivative. So we solve for things that are not inside derivative. In this case, I could solve for V1 or VC. I chose to solve for V1 from the first equation. V1 is VC over 4. Then I use that right here. So I get VC over 4 minus 7 VC minus 60 of that. And then I can multiply the whole thing by 4. Basically, I'm trying to put under the same denominator. And the last step is to normalize, and I get my differential equations. Okay, this is a standard process you're going to see over and over. I wanted to take time to do it on paper so that you don't see PowerPoint slide flying. And I'm also wanted to put this line that you see me put because that is how I want to see the outline of your work. Okay. And trust me, that will help you get the correct answer as well. So we're going to go back to the PowerPoint to essentially finish this problem here. Okay. So going back to the PowerPoint, this is the differential equation that we have. And again, no expectation you prove the solution to such differential equation. It's a standard differential equation, constant coefficient, 0 right-hand side. I just expect you to write the solution from that differential equation at that point. It's some constant A times e to the minus 90 divided by 80. Okay, and then I'm going to apply the initial condition at 0 because that's when the switch opens. And I'm going to say VC at 0. VC at 0 is equal to 4.8. Okay, and that gives me the value of A. And once I have VC, I can calculate I by simply dividing VC by the resistance 5 ohms. Okay, so again, I'm hoping, so again, if we plot these, that's what you get. Okay, So I'm hoping this particular solution really shows you how we handle a problem with a switch with one storage element. In this case, we have a capacitor, and with a source that's disconnecting from the circuit. So let me go back to the original statement of the problem here. Let me just clean up that line. So this is the original problem here. We're looking at one storage element, here a capacitor. We're looking at a source that at t equals 0 disconnect. So I know I have to solve the circuit for t less than 0 and for t greater than 0. Okay, so for t less than 0, the circuit is going to essentially be a DC circuit because everything is constant. So the capacitor is going to behave like an open. For t greater than 0, for t greater than 0, this part is going to be disconnected because the switch is going to disconnect it, and I'm going to have that other circuit. And just to show you what we do for that, I'll show you the work we did here. So that's when we went about carrying a nodal procedure to get the different. We could have done mesh. We went about carrying a nodal procedure to get the differential equation. And then from the differential equation again, we solve for V of C. We apply initial condition, and then we also can get I. That is the standard process. We're going to develop that muscle. Doesn't come naturally, folks. It comes with a little bit of practice, but I'm here and we're going to try to practice this. I thank you for your patience, and I'm hoping we'll do a little bit more in the next lecture.